Hello all, welcome to the next lecture of this course. In this lecture, we shall see how to automate CFD analysis for varying boundary condition or geometric parameters. Here, we have taken Rotor37 example, which we saw in first lecture. We have automated the back pressure, that is the static pressure at the outlet, so that it will generate the compressor performance points for different back pressures, that is from choke to surge. Choke is at lower back pressure and surge is at the maximum back pressure possible for this case. Here we can see the example of compressor characteristics where the pressure ratio keeps increasing and the mass flow keeps decreasing. So at the lowermost point the back pressure will be low, and as we increase the back pressure the pressure ratio will increase and mass flow rate decreases. This is the parametric analysis window. Here we can see set of design points, that is we have specified the RPM and we have varied the back pressure. It varies from 100 to 138, 140 back pressure, so that the results will be automatically generated for different back pressure cases. Using this mass flow and pressure ratio, we can generate the compressor characteristics. This is the mass flow versus pressure ratio plot. The left side is the analysis result and right side is the experimental results. This is the efficiency plot. Here efficiency is plotted with respect to mass flow rate, and here in the right side we can see the experimental results. Now we shall go to Workbench and see how to set up this parametric analysis case. Let us open Ansys Workbench and look for CFX. We can drag and drop CFX from the component systems. Now we shall import the case file of the Rotor37, which we did in first lecture. Right click setup and then import case. Now we shall edit setup and change the boundary conditions. In the CFX preprocessor, let us go to R1 outlet boundary. Here it is specified as outlet boundary, and in the boundary details we have specified a relative pressure as 1.3 atmosphere, that is the static pressure at the exit of the domain is 1.3 atmosphere. Now we shall give this as a parametric value, that is we can automatically change the back pressure so that it will generate the compressor characteristics. We shall specify this back pressure as an expression. Now go to expression and insert a new expression, that is back pressure. Here we can enter the value of back pressure as we shall start from 100 kilopascal. Please note the units are important here. It has to be mentioned within the square brackets. Click apply. Now the expression for back pressure is created. We shall go to outline, double click R1 outlet, go to boundary details. Let us enter the expression in this boundary condition. We can click this button to enter the expression. Right click, go to expressions and choose back pressure, which is equal to 100 kilopascal. Click OK. Now we can right click this expression and use it as a workbench input parameter. Let us go to workbench and then see how the case is looking. Now it has got setup, solution and results. We shall choose workbench input parameter for back pressure and see how it is looking. Click use as workbench input parameter. Here we can see a parameter set has been created. So in this parameter set we can double click and modify the back pressure value. Here it is 100 kilopascal for the first case. We can create for different back pressures and automate the analysis. Now we have specified 5 different back pressures from 100 to 140 kilopascal. So the workbench will generate the results for all 5 cases automatically. Here if we retain this particular retained data, it will store the result file as RES file inside the workbench folders. If we don't select this retained data, it will tabulate the results, but the results files will not be stored in the workbench folder. As of now, I am unchecking this value. Later, if required, we can select this retained data. Now let us go back to CFX preprocessor. Similar to back pressure, we can create expression for RPM also. Here we shall specify the RPM 17189 revolutions per minute. We can include this also as an workbench input parameter if required. So if we enable this, it will automatically generate the results for different RPMs as well as back pressure conditions. So by this method, we can generate the complete compressor characteristics from minimum to maximum speeds and lower pressure to higher back pressure. Now let us minimize preprocessor and go to Ansys Workbench. Here we can see all the variable parameters, that is back pressure and RPM. We can change the units to revolutions per minute. For this particular example, I will change only the back pressure and show the variation results. You can try to change the RPM value also and generate the compressor characteristics. Now we shall go to solution, right click and edit. We can start the run mode in local parallel. We can choose some 5 or 6 cores depending upon your resources. Now click start run. Now the solver has started. We can see the residuals here. Now the solver is complete. We can see the convergence of residuals here. We can also check the mass flow, pressure ratio, efficiency values here. Now let us go to Ansys post processor and then check the output parameters. Right click results and click edit. Here we can go to expressions and check the mass flow values at inlet, outlet and other parameters like pressure ratio, temperature ratio and efficiency. We can select these parameters which we have to monitor as workbench output parameter. Right click this and choose use as workbench output parameter. Once we select these workbench output parameters, we can see these values in the parameter table. Now let us go back to workbench. Here we can see the loop is complete. We shall click parameter set. Here we can see the output parameters like mass flow, in, out, pressure ratio, temperature ratio and efficiency. We can now select update all design points to update all the values. It will take the current solution as the initial file by default and then it will solve for all the back pressure conditions. Now we can click update points so that all the cases will be run automatically. We can retain the data if required. As of now, I am updating all the design points without retaining data. You can click OK to close all the editors. It will take quite some time to solve all the cases, so we can check the results after some time. Now we can see all the results are complete. We have got solutions for all the cases. But for the final case, that is 140 kilopascal back pressure, the solution has failed. The mass flow has become 0, pressure ratio, temperature ratio and efficiency, all the values have become 0. So it means this point is in surge location, that is there is no flow possible for this particular back pressure condition. So between 130 to 140 there may be some points in between which will have converged solution. So we shall run for 135 kilopascal as of now and update the design point. Now we can see for 135 kilopascal back pressure case, the solver has converged very well and we have got the mass flow and pressure ratio values. So there may be some more solutions between 135 and 140 kilopascal. We shall run for 2 more cases for 137 and 138 and we can solve the cases, update all design points. Now the other 2 cases are complete, that is for 137 and 138 kilopascal and we have got the results. Now we can plot them and check the compressor map. We shall arrange it by ascending. Now here we can click in this outline of parameters and then choose parameters chart. Double click this. We can hide the messages and progress bars. In the x-axis bottom, choose mass flow in, and in the y-axis you can choose pressure ratio. We can double click this. The compressor map is generated here. We can see the mass flow versus pressure ratio chart. We can delete the last point, that is 140 kilopascal point where the mass flow has become 0. Right click here and then delete the design point. Now we can see the other points and the compressor map. Also note that the points, that is 137 and 138 kilopascal, has got lower mass flow rate and slightly lower pressure ratio compared to the peak pressure ratio value. These points may not be actually true. So when we run the simulation for some more iterations, these points may fail. So we have to cautiously check the final points and then you have to run for some more iterations. We can also set the number of iterations as a parametric input in CFX preprocessor. So we can specify more number of iterations for the last 2 points. By this method, we can predict the compressor map more accurately. Another method is to specify mass flow boundary condition for the points near the surge region. That is the points near the higher back pressure zones. So where the pressure ratio will be almost flat but the mass flow rate will keep varying. Now let us go to CFX preprocessor and then see how to change the number of iterations as a parametric input. Go to project and open CFX preprocessor. Here we can go to solver control and we can see the maximum iterations here. We can click this checkbox, that is we can set this to workbench input parameter. Click and we can name it as maximum number of iterations. Click OK and then click OK. Now we can go back to workbench and see the parameter set. Here we can see maximum number of iterations as another additional input variable. We can change the number of iterations to a higher value so that we can find the surge point more accurately. By this method, we can automatically determine the compressor map or any other turbo component performance maps by specifying the input variable as a variable parameter. Please make a note that we can also change the dimensions of a particular geometry as an input parameter. For example, I will quickly show the demo for varying the dimensions. We can open the geometry, right click and edit in design modeler. We can create a simple sketch. For example, if we specify this dimension as 10 meter, we can give this as a variable parameter by clicking this checkbox. So it will be a variable parameter. We can specify the name here. Click OK. There should not be any space. Click OK. So this value will be reflected in the workbench parameter. You can see here. So I am deleting this. Okay, by this method, you can automate all the input variables and automate your simulations. Thanks for watching this video. I will see you in the next lecture.